Hey guys, so today we're going to be doing a little bit of a discussion about alkenes. I'll be going over the worksheet with you all and explaining a few concepts to you guys so that you can blow through this worksheet. I've been grading all of your reports. I still have a lot of emails from this week to reply to. You guys are doing extraordinarily well in your reports, and just like the stereochemistry worksheet, this alkene worksheet is only graded for completion. Do your best on it because all of these questions and concepts will be on your exam, and you'll need to do well on that in order to pass the class. So this is great practice. So let's dive right into it. Alrighty. So starting off right here. So let's see. So here's your worksheet. And right off at the top, it gives you a few examples of different alkenes. Not totally sure why, but Zach's an interesting guy, so we're not going to question him. So right off the bat, they give you a list of all of the different reactions that they want you to memorize and have ready for your exam. These are the concepts and reactions that you will be held responsible for knowing when exam time finally comes. And here they give you, oh wow, this is new. They didn't have this years ago. This just breaks down every single different reaction and shows exactly the reagents, the regioselectivity, and the stereoselectivity. That's amazing. So the difference between regioselectivity and stereoselectivity is, I'll find an example over here. Here's a great example. So regioselectivity would be more like where on, if you did a reaction on an alkene, say this one right here where my mouse is, which carbon would it attack? The one here or the two here? That's regioselectivity. Stereoselectivity is after it bonds, say you have a methyl that bonds here, and breaks this pi bond, so now it's a single bond, you have a methyl here, that is going to be an iodine there, let's say, that makes it a chiral carbon. So now you have to show the stereochemistry, you know, the wedges and dashes upon that carbon, show how it's chiral. So that's the difference between regioselectivity and stereoselectivity. Regioselectivity is where it attacks. Stereoselectivity is what geometric shape it takes after it has bonded. So moving back here, let's see here. Wow, these are really cool. I'll try and review a couple of these. I have something set up here similar, but I'll try and review a couple of these. This is all the same exact stuff. Dope. So then I'll just jump over here, no big deal. So first page of your worksheet is all naming, it always is every year, and then it's structures and you have to write the names. So we're going to go over nomenclature, which is very simple. You guys already know nomenclature, I'll just go over it now. You're just going to name from the double bond. So wherever the double bond starts is, you're going to start from the end of the chain that's closer to the end. So for here, you would just start on this carbon. On C, you would start right here with numbering and follow the longest carbon chain. And then, for example, let me find another example here that I like. That's another cool looking one. That's the same thing, pretty much just backwards. Oh, they literally are the same thing, but backwards. That's funny. You guys are going to end up naming it the same. Kind of redundant, but anyways. And then down here, you have the alkene way on this side. So you're going to start naming on this carbon here, and this OCH3 is going to be your methoxy group. So you're going to start naming on this carbon here, going in this direction, and it's going to be 1-methoxy, also the 1 alkene there. And speaking of regioselectivity, we'll go over E and Z real quick because he wants you to talk about that. So with the alkene, you can have E configuration and Z configuration. Now, what do I mean by that? Right here, actually. So E represents entgegen. It's German for opposite, different. So you can have a double bond where the two priority bonds coming off of it are facing opposite directions, like here. We call it trans double bond. So, or we would use the abbreviation in nomenclature as E for entgegen, the German term for different or opposite. Now, when you have two priority groups that are facing the same direction, like on this example on the left, we call it cis. So, or Z, zusammen. Zusammen just means same in German. So when you're naming an alkene where two priority groups are, two highest priority groups are going in the same direction, you call it cis. And when you're naming it, you can call it cis or you can call it Z. And over here, you call it trans or you would call it E. And then, as we spoke about before, these dashes and wedges are just referring to the stereochemistry, not to the regioselectivity. And for a lot of the multiple choice, you're going to have to read directly from the book, but Zach goes over all those concepts in lecture. But real quick, I'll go through each of the reactions that you guys need to know. So here's your alkene, and this is a very good example because on one side of the alkene, you have 2 carbons, on the other, you have 1 carbon and a proton. So you have one side that's priority over the other. So when we talk about something called Markovnikov and anti-Markovnikov, Markovnikov was a guy who came up with a naming system for the regioselectivity of alkenes. So which side certain reactions will prefer, the more stable, higher priority congested side, or the less stable side with substituent atoms surrounding it with lower priority. So in here, on the right side with 2 carbons, that'll be our higher priority, and on the left side, that'll be our lower priority. So for example, alcohols. So if we react, there are 2 different ways to add a hydroxy to the alkene here. And as you can see, one of them is anti-Markovnikov, adding the OH to the less substituted side, and one is Markovnikov, adding it to the more stable right side. So you can do regular hydration with acid, H2SO4, sulfuric acid, and water to attach it, or you can do oxymercuration, which uses water, and it's going to be mercury acetate with sodium borohydride. Now, when you use water with oxymercuration, you get the Markovnikov OH group attached. But when you use an alcohol with these same reagents, the sodium borohydride and the mercury acetate, you end up with an ether. See, oxymercuration, but alcohol instead of water. Alcohol instead of water. And this also follows Markovnikov. Now, another way to make an ether, similar to the hydration we spoke about with water and an acid H2SO4, if you use alcohol and an acid H2SO4, you'll get the ether equivalent, also Markovnikov. Now, since we're going to the left here, we'll go with ozonolysis, which is the next step. So we have an alkene here. Now, when you use ozone, O3, which is the substance that forms a nice layer just below the ionosphere in the sky, right above the stratosphere, that protects us from solar and cosmic rays from deep space. Now, ozonolysis will take the alkene and essentially you just draw a line right through the center double bonds here, and you cut it in half, and you attach an oxygen to either side. So you can see this alkene is being snapped in half and turned into 1 carbonyl and another carbonyl on the opposite side. And you can see this carbonyl has 2 carbons from that half of the alkene, and this carbonyl has 1 carbon from the other half of the alkene. Now you're going to use zinc and an acid to stabilize this reaction. It's just a reagent that goes with it, but that's not as important because anytime you see O3, you know it's ozonolysis and you know to cut this alkene in half. Now alkyl halides, you're going to use an acid as well, but remember, this is not hydration. You're not using sulfuric acid, you're using a halogen acid. Halogens are like bromine, chlorine, iodine, and fluorine. You're not going to see hydrofluoric acid, but you will often see, as here, hydrobromic, hydrochloric, and hydroiodic acid. So this follows Markovnikov and simply just adds a halogen to the more prioritized side of your alkene. Now, to do dihalogen, add 2 halogens at once, you'll see something like this, and you'll be Cl2 with CCl4, or it could be Br2 with CCl4, diiodide, I2 with CCl4. So CCl4 is the main reagent that goes with it. That's a carbon tetrachloride. And with that, you can add 2 halogens to either side of an alkene. Now, and they will add to the same side. That is important to know because it does not go over stereochemistry in these examples. Let me go back here. Maybe this little diagram he gave you does. Nope, it doesn't. Wow, isn't he great? Oh, it does over here. Oh, anti. All right, so scratch what I said before. I'm glad I checked because these, I had a feeling it might be, but the when you dihalogenate, so the 2 halogens are going to add opposites, similar to when you do hydrohalogenation. So you'll get the OH group and the halogen adding opposites, so anti, and that's just the stereochemistry. So if one was a dash, the other one would be a wedge, for example. You're not going to have them come into the same plane. That's more of a rare case. Like with osmium tetroxide, that adds vicinal diols that are syn in the same direction. looking for osmium tetroxide here. He didn't even use this example. So that's good that I went over that because osmium tetroxide will be on the exam. I guarantee it, it always is. And he didn't even put it on yet. So keep your eyes peeled for that. Osmium tetroxide, let's go back here. Osmium tetroxide, OSO4, adds 2 hydroxy to either side of the alkene, and they add to the same side. So they both be wedges, both be dashes, or both be straight lines, but they add to the same plane. This cyclopropane formation, you're not going to see this. This is a little more advanced. You're not going to see that on your exam. But just in case it's right here, it's just zinc copper with methyl iodide and your trichloromethane and potash or potassium hydroxide, KOH. Now to form epoxides, there's only one way to form epoxides, just like ozones. So ozonolysis uses ozone to form this, and see, anytime you see ozone, you know it's ozonolysis. Same thing with epoxides. Anytime you see MCPHS, epoxide, that stands for meta-chloroperoxybenzoic acid. So any peroxy acid can form an epoxide. And I'll show you what a peroxy acid is. It's just like an ester with an extra oxygen right here. See? So it's an ester, but or carboxylic acid in this case with an extra oxygen. Or here it's an ester, but with an extra oxygen, peroxy acid. And halohydrins, these also add Cl2 with water, so that's just your Cl2, Br2, or I2 with just water. Yeah, so NCS, NBS, and NIS, those are just basic additional reagents. You guys can ignore those for now. That's more advanced stuff. What's behind that little menu? I'm trying to read. I don't even flipping know. Oh, there we go. Oh, that's just catalytic hydrogenation. This is easy. So this is used palladium on carbon as a catalyst. So palladium is the catalyst, but it's attached to carbon because when you bond palladium to carbon, carbon is able to hold it and make it a little more organic, less inorganic, so that it can dissolve, go into solvents easier, organic solvents easier. And then you just use hydrogen gas. So you have a balloon of hydrogen or a compressed carbon fiber tank pushing hydrogen into a sealed system. And those are all the additive and oxidative cleavage reactions of alkenes. So what else we got here? Naming. So here's some more examples of naming. So you're going to start from the side with the alkene. Here's just a basic example. So here we have hexane otherwise, but we have a double bond and it's closer to the right side. So we start naming on the right side, hex 1-ene. You can also just call this, yeah, well, I guess hex 1-ene is a little more detailed. I would just go with that, hex-1-ene. The ene suffix is represents your alkene compound. So for here, again, you start on the right and you'll just form methyl hex 1-ene. And same thing, you start from the right and you just prioritize. Remember to prioritize by alphabetical. So for ethyl to methyl hex 1-ene. Meso compounds. What are meso compounds? They're essentially just compounds where they have at least 2 chiral centers, and that means that they're going to have 4 stereoisomers, and at least 2 of those stereoisomers are identical compounds, meaning, or at least they cancel each other out. They don't have chirality because you're able to rotate them about 1 bond and find a plane of symmetry. So here's a great example, finding planes of symmetry through bond rotations. So rotate 120 degrees Celsius, or 120, rotate 120 degrees, and here you get a nice meso compound where you can split it right down the middle. Here are some more examples. So one rotation, 120, another rotation of 60 degrees, you get another meso compound. And then here's an example with a Newman projection where you rotate 60 degrees, and then when you redraw it in its stick and ball twig formation, you can clearly see that it's a meso compound. So yeah, I would say the stick and ball formation, the dash wedge sawhorse, I guess it's called, is the best way to visualize if it's got a mirror image. Sometimes Fisher, but Fisher can be trickier because remember, if it's 3 chiral centers, then you're cutting right down the middle of a line, and remember these lines have stereochemistry. The ones horizontal lines come at you, and the top vertical lines go away from you. It's a very awkward form showing stereochemistry. But those are meso compounds, because I noticed that was on your worksheet, so, and I know it will be on your exam. Here's another great example of difference in naming between trans and cis. So D is just deuterium. It's just an isotope of hydrogen. It takes priority over hydrogen. It's just here to show example. So in this case, this on the right side here, this molecule, this right alkene is trans because we have our high priority D and our high priority C. So they're trans to one another. So it is E configuration. And on the left side, we have our D and our C. They are cis to one another. So it's cis. And so we're going to start counting from the left side, and we go 1Z, 3E, because this double bond is cis, Z, Zusammen, starts on the left side. So 1Z, 3, 1, 2, 3, third carbon starts E, entic again, opposite, trans. So 1Z, 3E, 1, 3, butadiene. And we say diene because it has two double bonds in it, so diene. And don't worry about this 1,4-D2 at the end. We only use the 1,4-D subscript 2 at the very end when you use isotopes in a compound. The isotopes in this case were just there to show priority. So we don't really need to go over the left side as much. But yeah, guys, this is naming, these are alkenes. Now, let me just make sure I didn't miss anything here. Yeah, catalytic hydrogenation isn't just palladium. Like I said, you can also see ruthenium, Ru, platinum, Pt, or nickel, Ni. And yes, the hydrogens add syn to one another, so they will be in the same stereochemistry plane. So either both dashes, both wedges, or both in the same plane. Anything else I'm missing here? Hydroboration oxidation. I don't know how I missed that one, but that's highly important. That's adding hydroxy. Oh, I did go over that here. See, I said it was anti-Markovnikov, but I didn't explain why. Hydroboration oxidation, very different than hydration or oxymercuration where you add the OH. It's also very different from hydrohalogenation where you add an OH and the osmium tetroxide dihydroxylation that you add. This is the only one, the only hydroxylation, adding a hydroxy group that's anti-Markovnikov, that will take the less priority side. The only one. That's how you can remember this. And it's hydroboration because it uses borane, BH3 here, in junction with hydrogen peroxide. So H2O2, because we know that the O single bonded to another O is the peroxide, as we went over before. So hydrogen peroxide. So borane with hydrogen peroxide and a base, NaOH, is hydroboration oxidation. You end up with anti-Markovnikov addition of hydroxy group, which is what is shown right here. Beautiful. And there are also other reagents that you could use. I think they're a little more advanced, but Zach apparently wants to use them. So 9-BBN is one way of doing anti-Markovnikov hydroboration oxidation that I don't think should be on this exam, but apparently it's going to be. And here he drew the structure of it for you. Like that's going to help. You guys will remember this. I know you will. I just want to make sure I didn't miss anything. Yep, and there's another great example of how each of these reactions will break down a cyclic alkene. See here with the ozonolysis, it breaks the alkene and we went from a cyclic compound to an acyclic compound. It's like this chain now. Notice how it's the only one that does that, by the way. That's important. And then here's your ridiculously long worksheet, guys. I do this worksheet every year. The first year I ever did it, it was really fun for me. But that's because I'm a weirdo. So, you know, just do as much as you can. I'm grading for completion, so just get at least half of it done, guys, and I'll give you credit. But you're going to need all this information to do well in the exam, or else none of this makes any sense because you won't pass. So there have been withdrawals. A lot of students have already withdrawn from the course, so it's not like a breeze, but I think you guys can do it. I think you guys will do just fine. So thanks for putting up with me once again. Another week has gone by, and good luck.